Okay. Does anybody have any questions? Are you all doing good? When, let's see, I'll pull up the chat for a minute. When you get done, Michael, Joshua, and Michael, and Tianhui, go ahead and just put done in the chat. And again, so let me talk to you, Michael Left. Michael Left, how you doing?
I'm good. How are you?
Pretty good, pretty good. So how does this one strike you? Are you making good progress on it, or
number 8? You mean?
Yeah.
Oh yeah. I'm done.
You're done. Okay. And what about you, Joshua?
Got it.
You got it. Okay. So okay, Michael. Why don't you tell us, what did you get first?
I got 9.74.
9.74. And what about you, Joshua?
Oh, I'm still working on it. I'm not done yet.
Okay. Do you need help?
No, I think I just need more time. I think I got my budget line and the tangency right now, but I haven't solved it yet.
but check it out. You're working too hard, right? Because it already gives you the consumption bundle that he's consuming in this one, right? It doesn't ask you to compute his optimal consumption bundle, which is what you're working on.
Oh, gotcha. Yeah, I looked over that. Sorry.
Yeah, so this is, yeah, like these questions, a lot of them are, you know, related. They'll have like the same parameters and stuff like that. And that's intentional so that you can kind of get a roll if you're working on one. But also there are some of them that it gives you all the information, but a lot of it's irrelevant information. You don't really need it. So you have to, you know, look kind of carefully. So, okay. And what about Michael Barbie? How are you doing on 9?
Still working on it.
Okay. Do you have a question? Are you?
For the Cobb-Douglas utility function, it's x to the alpha, y to the 1 minus alpha. For the x value, am I putting in 8 times 6 or 8 times 4?
Yeah. So that's a good question. So look here, right? So what you're talking about is that, you know, and they're just variable names, so we can name them whatever we want, right? So let me do this really quickly. So our alpha here is 12 over 100, right? Or 0.12. And we're talking about tacos and tequila. So let me do a new share. I'll do the whiteboard here. And I'm gonna have to put down the chat and close that up. Okay. So can you see the whiteboard now, Michael?
Yes.
Okay, good. So I'm gonna try to, because it's hard to do it with subscripts and superscripts because we don't really have the tools for that. Oh, wait a minute. Delete So I got to write it like this. So we have generally U, and notice, right? I don't know. So Michael, you've done probably like 3-dimensional functions before, right? So normally you would have some Z, this would be your Z axis, is equal to some function of X and Y. Those are your general axes labels. Does that make sense? And then we'd be drawing something like this. Are you following me, Michael?
Yeah.
Right. So like this, where we would have an x-axis and y-axis and a z-axis, right? So, but here we're graphing utility on the z-axis. So then we have what we're going to graph on that first horizontal axis, x raised to, I'm just going to say to the a instead of alpha because I don't have alpha here, times y raised to the beta power, where what you said is true, beta is equal to 1 minus alpha. And so the way that we interpret alpha and beta are as percentages. So, and in our problem, I'm trying to get this so I can move it a little bit. There we go. Does that make sense, Michael?
Yeah, so far.
Yeah, so we would have U, and X and Y are just consumption goods. In this case, if we want to graph X on the first horizontal axis, so it'll be tacos raised to the 0.12 power, right? And we can kind of be explicit and put some like brackets around it, times tequila, right? Raised to, in this case, it would be, what would be the power? 0. what?
88.
88, yeah. So then we just have to put in whatever our quantities. This is the quantity of tacos consumed and the quantity of tequila consumed. And then we can calculate the utility associated with that point on our 3-dimensional graph. So in this case, we have U is equal to, how many tacos are there? 10? Or I forget.
In my problem, it was 8.
Okay, 8 tacos raised to the 0. Okay. 0.12 power times, and how many shots of tequila?
It was 10. 10
to the, raised to the 0.88 power. And then we'll get some number. And you can tell me what about you, Tian Hui? Did you get this? Does this make sense to you? Do you have your number?
No.
Okay. Do you follow what we're doing?
Yes.
Okay. So, okay. Then I'll rely on you, Michael Burby, to give us your number. What did you end up computing?
I got 9.74.
9.74. Okay, Tian Hui, why don't you go ahead and do the calculation and see if you agree with Michael. He said it's 9.7.
9.76.
Oh, you got 9.76, so a little bit different. Okay, I don't know if there's some rounding error in there or not, but we can check it out in just a minute. So do you get the way the graph would look for this point? So we would have some point here on the tacos axis. Let's say that's 8, right? And then we're going to have some point on the tequila axis. Let me see if I can get it. 10, right? And so there's going to be some point out here in this plane. I'm going to try to identify it. Is this starting to look like okay, Michael?
Yeah, it does.
Yeah. So we have this point in this plane, and it's corresponding to a height on the z-axis, which is on our function. And so does that look all right to you, Tian Hui?
Yes.
So this is going to be up here some height, and to that point, and let's try to give it I'll give it a pink color. So that point up here corresponds to a value in this z dimension of 9.74. Okay. Now that's just one point on this surface. And again, if you watch the videos, you'll be able to see that. But that's what you guys just calculated, 9.74. And let's go ahead and go back to Ignitium. Okay. Now, so our other team, so Joshua, what did you get for number 8?
I actually ended up at a roadblock. I'm not too sure how to solve this.
Okay, well, did you just see what we did? It's the exact same thing. It's just you're taking, in your case, right? It's the same utility function, right? It's to the 0.12 power and the 0.88 power, right? Because that's your alpha. Your alpha is still 12 over 100, isn't it? Or
Yeah,
no,
it's 12 over 100.
Yeah. So it's this exact same utility function. Do you see what I'm talking about right here?
Yeah.
And you just have to put in your consumption bundle, which I think, what did you have? 14 tacos? I don't know how many shots of tequila. And then you'll get some number out, which is the utility, the value of the utility function at that point in the domain of the utility function, which is this consumption bundle. Does that make sense?
Yeah, maybe I did figure it out then. I was thinking of what Michael got for the first time around. I think I got like a different number, so.
Well, that's okay. That's why we have multiple.
Yeah, so I didn't think I did it right.
Okay, so do you want to tell us what your answer is for number 8, Joshua?
Well, so not sure it's right, but I got 11.48 doing 8 to the power of 0.12, then 14 to 0.88.
And okay, so Michael left. Are you revising your answer, or are you sticking with it?
I'm sorry?
Are you revising your answer, or are you sticking with it?
Oh, yeah, it turns out I was doing number 9.
Oh,
Yeah, so that
okay.
explains the error.
Okay. So you agree.
Yeah, I'm sure it
Boy.
is.
Okay. So you both didn't end up with quite the right answer. I wonder why that is. Should we go ahead and run through the calculation then? Well, let's go ahead and check the other one. 9.74. Okay. So team 2, we do an applause for. And team 1, do you all want to check your calculation and see?
I think that'd be a good idea.
Yeah. So we'll go back to the whiteboard. So you two have to make sure that, so I'm doing the math correctly. So we'll just work off of this example. So how many tacos was it again?
8 tacos.
It was 8 tacos for
Yes.
8 for, okay, hold on. Okay, I have, 8 tacos and 14 shots of tequila. Okay, so, okay, and so the only thing that changes here is this. Okay. Now, I'm using my scientific calculator on my phone, and I get 8 raised to the 0.12 power. And I get that to be 1.2834. Okay. So $1.2834 times. Okay. And I'm going to do 14 raised to the 0.88 power. And I get 10. Well, so now, right, 10.1998. All right. Are you following, Joshua?
Yeah, I think I see what happened. I think I pressed add, not multiply. So I ended up with 11 and not 13.
Yeah, okay. So, so I'll do the equals and times 1.2834. Yeah, and I get the answer that Ignatian computed. Okay. So now I'll ask, does anybody have any question on either of those? No questions? Okay. So let's go ahead and move on. Number 10. Oh, well, we could do this. This is exactly the same thing. We're just computing a different point, right? So there should be no question about that. So for 11, let's go ahead. Arslan, how are you doing?
Doing good.
Good. Okay. So what about question number 11? What does this mean to you?
Can I see it? It's still on the whiteboard.
Oh, hold on a minute. New share. Yeah, sure. I'll show you the question. Can you see it now? Oh, hold on. There.
Now I can, yeah.
Yeah. Okay, how's that?
Good. Give me a sec to look at it. So with this one, do you just ignore the Cobb-Douglas function and focus on the price and the budget?
Well, okay, good question, right? So and Nutanicha, are you here too? Nutanicha?
Yes.
Okay. So why don't you help us out with number 11 too? So so tell me what you're thinking, Arslan. What's this question asking us to do?
It's asking us to find out how many shots of tequila you purchased in Mexico.
Yeah. So and what do you think? How would you approach that problem? I don't know if there's anything echoed from anything you saw in any of the lectures yet, but it's kind of a new problem. How would you characterize this? Is it about how many shots he could afford?
It's not how many shots you can afford. It's how many shots did you buy exactly?
Yeah, and is it about how many shots that he wanted?
No, just how many you purchased.
Yeah,
I think we all purchase more than we want when it comes to
it's a prediction, right, of his behavior. Yeah. What did he actually do? Right?
Yeah.
And do you see that, Nietzsche? Do you agree with Arslan and I?
Yeah.
That's what the question's asking. So how in economics, this is kind of a really, really important overarching point. In economics, how do we predict human behavior in these settings? But to be clear, economics is pretty much a comprehensive tool or approach for predicting human behavior. There's a lot of fascinating applications of economics out there that deal with everything from Arslan, do you do chores around your house? Do you like take out the trash and help out with the lawn or anything, or walk the dog?
Yep.
If you have a dog, I don't know, walk the cat.
We have a cat. Oh. She walks herself.
But somebody's got to empty the litter box, or is she an indoor-outdoor cat that just comes?
She's an indoor-outdoor cat.
Oh, that's even nice. She have a little cat door, or does she just meow when she wants out?
You know what? She taps on my window in the middle of the night to wake me up. To get inside.
To get inside, right? Yeah. What about when she wants out, or does she just follow you guys?
Same thing. She'll stick her hand under my door. She likes to leave through my window. That's her preferred.
Yeah, I've had some good cats in my time too. And what about you, Nudanicha? Do you help out with stuff around the house? Do you wash the car, or fill up the gas tank, or do anything to help your family out, or I don't know if you live with your family or if you have roommates or what?
Yeah, I did something.
You do some things, yeah. Well, so there are economic models about how people share chores in the household. There's economic models about how criminals choose which crimes to commit, right? And should I do armed robbery, or should I do unarmed robbery? Should I commit battery, or should I sell drugs, right? So, but what do they all have in common? Do you have an idea, Arslan? Or Newton-Nietzsche?
I think it's that they choose what they want.
Oh, but see, what they want is their preferences, right?
Yeah.
Yeah, like, so, but that's like kind of like the same for everybody, right? It's I mean, like, not that everybody has the same preferences, but like for like a lot of us, I don't know about you, but my preferences are such that I would be. Do you ever, I don't know where you all live, but I live in Fullerton, and during the summer, I frequently go down to Newport Beach. I don't know if if you get off at MacArthur there by Fashion Island, if you go down to PCH, do you know where I'm talking about?
Yeah, I do.
Yeah. So you can turn on a little street called Poppy, and then there's this beach. I think they call it Little Corona, and you can go down there, and it's really nice. And there are these beautiful houses, and if you know, my preferences were all that mattered, I would be living down at Little Corona in one of those huge houses overlooking the Pacific Ocean. And they're probably, I bet you a lot of you would probably be down there with me. Where would you live, Arslan?
That sounds pretty good to me too.
What about you, Nutanicha? Where would you pick?
Maybe. Yeah. Somewhere in Laguna Beach.
Oh, somewhere in Laguna Beach. Okay, yeah, Laguna Beach is nice too. Okay, some people are beach people, other people are mountain people, but there's more than preferences at work here, right? What else is going on?
Budget, fact.
Yeah, you have a constrained choice set, right, based on what's affordable to you. So the way that economists say it is that all of these individuals that we're talking about, whether it's the criminal or the people in their household, or the example here of, you know, the taco and tequila purchaser, they have preferences of what they would want if they could choose whatever they wanted, if there were no constraints, right? And that influences their behavior somewhat. They go in the direction, right? Like for me, if I think about buying a new house and I live in Fullerton, you know, I'm probably more likely to move closer to Newport than further away, right? But there's also the issue of the constraint, their budget. So we say that all consumers are trying to do and all individuals are trying to do what's optimal, what's best for them considering their constraints, right? So that's the key prediction, is that rational individuals will choose to do what's best for themselves. And another way of saying choosing what's best is to say that they're going to behave optimally. Does that make sense, Nutanicha and Arslan?
Yeah, that makes sense.
Yeah. What do you think, Nutanicha? What's that?
Can you repeat that again?
Yeah, I'm just saying that our prediction is that people will do what's best for them,
yeah.
right, given their situation. And another way of saying that is to say they behave optimally and with respect to any situation they find themselves in. They do what's best for themselves. And in these sort of simple settings where they're trying to choose a consumption bundle out of a bunch of different possible consumption bundles, we kind of narrow it down more. Our consumer choice problem is solved through utility maximization subject to constraints on their budget. So that's kind of the only reason why I talked you to this point is that, you know, what you often hear in textbooks and out of professors' mouths are simply that, you know, we're going to do a consumer optimization problem, or the consumer is going to maximize their utility subject to their budget. And they never talk about, well, this more real world kind of idea that people have preferences, they have constraints, and those preferences represent what they want, their idea of what's best for them, what would make them happiest. That's what utility is about. Utility. Here's another thing. You know, there's another name that has historically been used for the utility function. Arslan, can you guess what it is?
Happiness.
Well, yeah, they've called it the Felicity function. And felicity is another word for happiness, right?
Yeah.
Yeah. So we're saying that people are behaving optimally in the sense that they're choosing what from their point of view will get them the most happiness of all the choices that they have available. Now, the reason why I kind of walk us through a little bit of the intuition behind utility maximization is because once we've gotten to the point where we've decided that consumers are going to behave optimally, all of this becomes very mechanistic, right? We have a way of solving once we think we've represented these preferences and the budget constraint mathematically well, then within that representation, we just churn through and we get this optimal consumption bundle. And you would be surprised how many students can solve the optimal consumption bundle. But if you ask them just a simple question like, well, then how many, given all this information, what does your professor actually choose to do? Then they completely lose it because they don't understand that the mathematics is a prediction of what a real life person will choose to do. So, and isn't that, I don't know about you, but Arslan, I think that that's kind of funny that somebody can do all the math perfectly, but when you ask them, okay, in simple terms, like, what does this mean? What's somebody going to choose? They just melt down. So does that make me cruel, Arslan, or?
No, I mean, it seems like a good thing to know because you're right. Like it would seem easier to just solve it instead of breaking down like what exactly you're solving.
Yeah, well, and what does it mean in the real world? Because if all you ever see when you see these problems is a problem to be solved and no real world manifestation of what inspired the problem, then you're never going to be able to take these results outside of this homework set. You're never going to, because nobody's ever going to come to you in an analyst position and say, hey, you know what, Arslan? Solve me a utility maximization problem, right?
Yeah.
What's going to happen is you're going to be working for Tito's Tequila, and they're going to say, "Hey, how many shots of tequila do you think that the average person is going to buy down in Cancun this summer? Can you give us a best estimate?" Right? That's what
that sounds much more real world for sure.
Yeah, that's what they're going to ask you to do, and you're going to have to say like, oh wow, like, okay, I need some information. What kind of information do I need? Well, I need to know something about what price we're going to charge. I need to know something about how is that price relative to the affordability of what a person spends on their vacation. Also, what alternative goods, right, like tacos, right, might they spend that budget on, and then something about their preferences. And then you could begin to put together some sort of a survey, and you could use statistical methods to estimate these values. I mean, you'll know the price of tacos and tequila, but you might not know, what's a family budget for their vacation, or a person's budget for their vacation. I mean, I just got back from Mammoth last, Thursday, Friday, and I had a budget in mind for my vacation.
Professor, I have a question.
Go ahead.
So how exactly would you calculate the maximum utility for problem 11?
Yeah. So this is where we're going, and that's what I wanted to. I just wanted to set up the problem so we would know. So So, okay, we got to go back to the whiteboard. Okay. So, and you know what I'm going to do? Hold on a minute. Let me go back here and I'll grab the problem. So I'm assuming Arslan and Tian Hui that you all don't really have a suggestion for how to solve it yet. Is that right? Or
not yet. I mean, now that we've talked about it, I would assume we need the utility function and then we'd solve for tequila, like the quantity of tequila.
Yeah, sort of, right? But to be more precise, let's start a new whiteboard. And this is explained in great detail in the lectures that you guys will be viewing this week. But since we're trying to get to the nub of things, we end up having two simultaneous equations, a system of equations, and one of them is just the budget, because that describes their constraint, right? So we have this general notion, and let me go ahead and put this over here. Okay, so there's our budget, right? So, and we represented our budget as px times x plus py times y. And I think Michael Left was the one that answered the question. So does this make sense to you so far, Michael?
Yeah.
Yeah, because I think you were the one that asked. You're like, oh, okay, so how do we actually do this, right? So it says, how many shots of tequila does your professor purchase? And I think this one is asking about before the price change. Okay, so we're going to go with his budget before the price change. And you can see that the price of tacos is 16. Since I'm going to graph tacos on the x-axis, I'm going to use x as tacos. So 16x plus, and it says 66 pesos for a shot of tequila. So there I have the budget, right? And the other equation, so when you all see this, hopefully, Arslan, you see something that looks like a supplier demand equation, right? So do you have echoes of that here?
Yeah, if we push the y to the other side.
Yeah, right. So, right, exactly. So it's a general linear equation, and we can write a linear equation in slope-intercept form. And then, lo and behold, we have something that just looks like a supplier demand curve. Now, this one is going to be a little bit different. And so the tangency condition is that the marginal rate of substitution is equal to the price ratio, okay? And we haven't talked about it yet, but this is the second equation. And hopefully, and I don't know if this makes sense to you, and I'll kind of clean this up a little bit. And the marginal rate of substitution is some general, but it turns out it's a non-linear function. So I'm just going to write, it's some function of x and y. Okay. But and tell me, Arslan, if you can see this, right? So I have an equation in terms of x and y here, and I have an equation in terms of x and y there, right? And so if it was just like this is supply and this is demand, then they would be two linear equations, and the simultaneous equation solution would give me the point, the value of x and the value of y that satisfies both these equations at the same time, right?
Sure.
And that would be the point where demand and supply cross. Okay. So we have one of those equations, and then this would just be a simple matter of, you know, I think I mentioned this before. Do you remember the technique, what it's called when you have two simultaneous equations and you solve the system, the one that most people use?
Not sure I remember right now.
Yeah, well, we call it substitution and elimination. That's the technique where, you know, like you set one of the values equal to another value here, and then you end up with one equation in terms of just one of the variables, and then you can solve it and then substitute it back into the original one. But now that I've described it, the technique, right? That's what you have been doing when you've been finding equilibrium, right?
Yeah.
Yeah. So here, it's a little bit different. You are going to still use substitution and elimination, but because this function f is nonlinear, things are going to look a little bit different. But our key here is understanding the marginal rate of substitution. Okay. So let's talk a little bit about that. Well, okay. So what we're going to do is, and remember that our utility function is really three-dimensional, right? And so we're graphing utility on the z-axis, and then we have some quantity of two different goods that we purchase, x and y. But what you're going to be doing most of the time is you're going to be looking at a graph that's only a two-dimensional representation of the three-dimensional utility function. So we're just going to show you the x and the y plane. So let's just say this is, for being concrete, tacos, okay? And then y is tequila, but I won't label that. And then the first thing that you're gonna do is you're gonna graph the budget constraint. And does this look familiar from the videos? I think this is discussed in one of the videos I assigned you last week. And then I'm going to be looking at one, what we call indifference curve. And it should be C-shaped, but I kind of goofed it up a little bit there. So try to correct it. And this point of tangency between the, oh, hold on, let me get this better. This point of tangency between the budget line and a particular indifference curve. See, the issue is that we don't know and I'll put this as a question mark. We don't know what indifference curve this is yet. And that's the reason why we can't just, go ahead and like draw the picture and be done. But that point of tangency is going to identify a certain amount of X and a certain amount of Y. Okay. And that's going to be our X star and our Y star. And X star and Y star, once they're determined, kind of like Q star and P star, right, from our equilibrium problems, that's going to be the consumer's optimal consumption bundle. It's going to represent the amount of X and Y. And does all this, is this language making sense to you? Because some of it, again, is mentioned in those videos, but Arslan and Michael left because you asked, is it making sense? We're looking for a consumption bundle. Consumption bundle consists of a specific quantity of each of the goods that the consumer consumes. And X star and Y star, since we only have two goods in this case, represent a particular consumption bundle, which is a consumer's optimal consumption bundle. Does that all, are you fine
Yeah,
with
that makes
or?
sense. I'm just asking like how would you solve for X star and Y star?
Yeah. So okay. So, well, and the reason why I'm going through this, and hopefully this makes sense, Michael, is that we're all good right here, right? We just have two equations and two unknowns, but our problem is that we don't really understand the MRS yet, right? The marginal rate of substitution. And so that's why we're kind of talking our way through this. Okay. Now, it turns out that generally, the marginal rate of substitution has the following form. Okay. So I'll say generally, the MRS is equal to the marginal utility of X divided by the marginal utility of Y. Okay. And I say this generally because this is the sort of thing, like if I was looking for a solution on a test and you guys were documenting your work, I would want you to write what I have here. We have our budget condition, and then you would give your budget constraint. And we have our tangency condition, which is, the marginal rate of substitution is equal to the price ratio. And I have asked students in the past to calculate the marginal utility of X and the marginal utility of Y. But it turns out that one of the reasons why we use Cobb-Douglas is a very useful utility function, meaning that it has wide application in a lot of economic models out there. So it's not literally just a toy for us to learn how to solve these problems, but it has a particular type of mathematical simplicity that makes it very, very useful for learning utility maximization. It turns out that the marginal rate of substitution in the case of the Cobb-Douglas is just alpha Y over beta X. And so here, then we have the prices already. The price of X is 16 over 66. And So I'll just write this one more time, px over py. And then hopefully this makes sense. Here, our alpha is, can you see that, Michael, left? It's 19 over 100. So our problem's a little bit different, right? Michael?
Yeah, so alpha is really just a measure of marginal utility.
Well, no, but I said, because we haven't gone through it yet, I'm kind of skipping to the end part, but it just turns out that there's enough symmetry in the set of equations that when you calculate the marginal utilities of X and Y and you take their ratio, then you end up with this really compact expression. And so that's stuff that's, again, explained in the video lectures, and we'll have time to talk about, you know, as we go forward in the lectures. But to kind of like, you know, answer your question, this is ultimately what you would end up doing is, so I'm going to write it with a capital X. So you see where I'm getting these numbers from now, Michael?
Yeah, it's just.
So these are our two simultaneous equations, that one and this one. And then we just use substitution and elimination, and we find the X and Y that satisfies both of them.
And so
and that's our X star and our Y star.
So just the alpha Y over beta Y was derived.
over beta. Oh, sorry, I typed it wrong. Alpha Y over beta X. Sorry.
Right. Okay. So that was derived from something that's more advanced than this course, if I'm understanding that correctly, right?
Well, no, it's not more advanced in this course. We're going to talk about it.
It's just
and
layer.
It's just that you know, I think that your question, particularly because we're trying to solve this particular problem, is we really want to focus on, okay, what are the elements we need to solve this problem? We need these two equations. We know where this one comes from. And now you do know where this one comes from, but you don't really understand what's the relationship between the marginal rate of substitution and the price ratio. That's
I understand the MRS equals P of X over P of Y. I just don't understand the alpha Y over beta X.
Yeah. Well, if you do understand this, and you understand that marginal rate of substitution is this, then it's just a matter of calculation, algebra, and a little bit of calculus to get you from here to here. Okay. So we have these two equations, and from the problem, we're going to get this, and we're going to get that. And then we have our two simultaneous equations, and we'll take one and substitute into the other, and solve our problem. So to go ahead and bring this full circle, I'm going to go ahead and let's just do the math really quickly over here. Okay, so I'm going to put this in red. So we have 750 is equal to 16x plus 66y, right? And then this is the point in time where, you know, I would get out my handy dandy calculator, and so I'm gonna have 66 16 divided by 66, I get 0.242424, right? And then what I would do is I would go ahead and move the 0.81x over to the other side, right? Multiply both sides by 0.81x. And then I would divide both sides by 0.19. And then that would be my representation for that last equation. I would have y by itself is equal to, so let me do equals and then times 0.81 and then divided by 0.19, and I get 1.0334x. So Michael and Arslan and Joshua, do you guys want to verify that you agree with me? You guys can check my algebra that that this equation translates to that when you simplify it a little bit.
I mean, yeah, I mean, like I understand the math behind it. You just solve for y and then plug into the other equation.
Yeah,
So
but I'm asking you to use your calculator and agree with me.
Yeah, I calculated again and it worked out.
Okay. So and you are Arslan. If we get consensus on this, because it's really easy for me to press the wrong button like anybody else on the calculator.
Yeah, no, sorry. I'm actually still a little stuck on getting that y value.
Yeah.
So we're doing the. Oh, go ahead, please.
Yeah, so it's down here, Arslan. You see?
Yeah.
I got 16. When you put in your calculator? 16 divided by
0.24 for that.
0.24. Yeah. 0.24242424, right?
Mm-hmm.
And then 0.81x. I'm multiplying both sides by that. So you get 0.24242424 times 0.81 for the coefficient, right?
Yeah.
And you get 0.19.
Okay. Yeah, I got it.
And then you divide. And then you divide by 0.19, right?
Yep, I got it.
Okay, so everybody agrees here, right?
Yeah, and then
then you can see it gets super simple all of a sudden, right? Then I just take this y and I plug it in there and I get one equation in terms of x, and then I solve for x and I get x star. So Arslan, Joshua, and Michael left. How about I let you do that for 5 minutes and then tell me what x star and y star is, and then we'll go back and check it, okay?
So what exactly is alpha then?
Well, we can talk about that in a minute, but do the math first, okay? And then we'll talk. Because now you're going back to Michael. You were saying before, okay, show me how to solve this problem, and now you're like, but what does it mean? Which is totally fine. You know, I actually, what I enjoy most about economics is figuring out whether or not the math represents something that's sensible. So I love to talk with you about it, but go ahead and just crunch through the math and I'll be back in 5 minutes, okay? Oh, there are no questions about the math, right, Michael?
No.
Okay. Okay, so Arslan, Michael, and Joshua, how are you all doing?
Good.
Okay, so do you all have an answer?
Yeah, I have an answer. I
So
got
for
8 point. Oh, go ahead, please.
Yeah, go ahead. So you're going to say for X star, which is the tacos, you got what?
8.503.
8.503. Do you, Joshua and Michael agree?
I got something a bit higher, but still close. I got 8.907.
Oh, that seems way off, honestly. That's like a whole half a taco. So, and what about you, Michael?
Yeah, I got 8.9069.
9069. Okay. So somebody, do you want to recheck, Arslan?
I don't know. I'm kind of confident in mine, but it is 2 versus 1.
Okay. Well, let's okay, I'll do it with you. Okay, it's pretty easy, right? So if I got the 1.034, and it's still in my calculator, so I have like 92882, whatever. Okay, if I do that times 66, I get 68.2105 X. So my next step here would be, if I was going to be, is equal to 16x plus 68.2105x.
Yeah, I think I just got a rounding error right there. That's all. Because I got 68.2044.
Yeah, but still, that even seems pretty close. But let's see. All right. So I'm going to do that plus 16. And obviously, I get 84.21, right? And then, so then I'll do 750 divided by 84 point, I'm just going to do 21. And I get 8.906. So you had 750 divided by what, Arslan?
Divided by 84.2044.
Yeah,
so just a little bit off.
84.2044. And you still get that 8.9066. 9689. So I think you probably misspoke.
I did misspeak, yeah.
Okay.
I entered the wrong thing. It's early.
So,
I'm sorry.
Okay. So let's go to our Emithium. And we were working on number 11, right? And we said 9.2. Huh. Were we working on number 11?
We were doing number 11, but we solved for X star. And I think the equation wants Y star.
Yeah,
No.
if you multiply the 1.0334 by the 8.9069, you get 9.2043 such and such.
16 is going to get to 15. So many little screens all over my big screen. Okay. Yeah, that's 11. So we shouldn't be off that much. There has to be, because it's tacos we're solving for, and we used for our taco parameter, which is alpha.
Professor, I think we're solving for tequila.
Oh yeah, duh. Right. So, okay. Yeah, it is early for me, right? Okay. How much has the tequila, right? So now we have our X star, which is, what did we say it was, Arslan? 8.9.
907, I guess.
Zero. Okay, I'll just 64. Okay. And then we just put that back into our original equation right up here. And then we can solve for y, right? So I'll do 750 is equal to 16 times 8.9064 plus 66y. And okay, so 16 times 8.9064, and I get 142.50, right? So this is going to be 750 minus 142.5024, right? It's equal to 66y. I'm only going through the details of the algebra because this is like our first time doing it. You know, if you don't want to be quite so detailed in your explanations, as long as I can follow from line to line, it's not a big deal. And so minus 750 is equal, and I get 607.4976. So divided by 607.49 divided by 66. And I get, yeah, 9.02. Yay. So y star is equal to 607.49 divided by 66 is equal to 9.20. I think we all deserve a clap. So does that make sense? Is everybody good? Are there any questions? Arslan? Joshua? Anybody else? I forget who else chimed in and saved us or reminded us that it was tequila. But I recognize the voice.
It was me, Professor.
Who is that?
Mike Bardet.
Emilio? Oh, okay. Thank you. Thanks for helping us with that. So, Mike Barbie. So, but does anybody have any questions?
Yeah, Professor, when does the change in taco price come into play?
Well, okay. So, a little bit later, but let's go ahead and take a look here to new. Share. And so this is before the price change, right? Here, this should actually have said how many blah, blah, blah. It should say before the price change because we just used the prices before. Well, I guess it doesn't matter, right? Because it's tequila and the tequila price doesn't change. So we're fine. But still, yeah. It presumably it could matter, but it turns out not to. So we're talking about tequila, so there's no ambiguity in the price issue. By the way, I'll tell you, this is a little, you know, if you did it yourself, you'd figure this out. But the price of the tacos changing doesn't change the amount of tequila that he purchases. That's one of the features of the Cobb-Douglas utility function. But so here when we're talking about tacos, we have to be explicit before the price change. Before the price change. Do you see, Joshua?
Yeah.
Before the price change. But then we get down to number 15 and it asks us after the price change. Okay. And you might be a little bit, it turns out that we're going to spend most of our time down here on questions 19 and 20. But in order for us to talk about 1920, we have to have all this other stuff out of the way. One of the big ideas looming in the background that we won't get a chance to talk about until next week, because Thursday we have our exam. So I'm getting ready to transition us out of talking about this stuff. But what our real issue is we want to understand demand. So there are a couple of things I want to show you all. So now everybody should be able to solve all of the problems down to problem 18. Okay, it's only the last two problems that you can't solve. Not that you understand everything perfectly, because we still haven't really talked about marginal utility and all that stuff. Again, it's in the videos, but I can talk about it a little bit in some of our face-to-face sessions too. But let's go ahead and go back to the whiteboard for a minute. And so what's going on here? So we have found our optimal consumption bundle in this particular example. We found our X star and our Y star. And what we really want to do is, if you understand this kind of graph, and by the way, one of the things that we're going to want to do is once we find X star and Y star, we're going to want to plug it back into our utility function to find the consumer's optimal level of utility, what level of utility they achieve, U star. So there's another kind of, you know, piece to this. But ultimately, what we want to do is we want to show that the utility function provides all of the data that we need to estimate the consumer's demand function. Okay. And the way that we do that is we do, if you think about demand, right? And to be clear about it, there are a couple different ways to represent demand. The demand curve that you all are familiar with, the one that we use in Principles of Economics, is called the Marshallian demand function, and after Alfred Marshall. And the Marshallian demand function is a price income consumption function. So what it does is it shows holding the consumer's income constant as you change the price of a good. And specifically, we're holding their nominal income constant. Arslan, I think I talked with you about this, or maybe it was Joshua, but do you remember the difference between nominal and real? That when we're talking about nominal stuff, we're just talking about the dollar value, right?
Yeah.
Yeah, in terms of dollar.
Yeah, so when I say I'm holding your nominal income constant, that should, in your mind, mean, oh, he means like, you know, my income is $3,000 a month. It's a dollar value, right? But I could also talk about trying to hold your real income constant, which is your purchasing power, right? It's like your inflation adjusted value of your income. So hopefully that, you know, there's some, you know, idea that if I was going to say I'm going to hold your real income constant, that would be a different idea than nominal income. That makes sense?
That makes sense. Yeah.
Okay. So the Marshallian demand curve is derived by holding the consumer's nominal income constant. So we're going to have an equation where I is a particular value, and then we have px plus py times y. And we're gonna, if we're gonna talk about the demand for x, right? So x is tomatoes or tacos or whatever. We're gonna let the dollar price, right, the nominal price of tacos change. And so when you guys think about demand, the way that we've been talking about it, I would ask you things like, oh, if the price of tacos increases, you know, from $2 a taco to $5 a taco, how does the consumer's quantity demanded change? Does that make sense? Michael left.
Yeah.
Yeah. So graphically in our consumer choice problem, the way, if we had a decrease in the price of tacos and we held I income constant, right? The way that we would represent that would be by just this rotation outward of the budget constraint.
And this is if the price decreases, correct?
Yeah. So a price decreasing would be a rotation outward because now more X becomes affordable, right? As we decrease the price of X, holding income constant. If your income is like $3,000 and I lower the price of tacos from $5 a taco to $2 a taco, you can afford more tacos, right? So that's how our graph would change. Obviously, if I increase the price of tacos, we would have exactly the opposite situation, right? You'd have a rotation inward of the budget line. Does that make sense? Arslan, Joshua, you guys have been talking to me. Michael left, Michael Barbie. Are you good?
Yeah, that makes sense.
Yeah.
So in terms of our consumer choice problem, right? When the price changes, we get a new consumer choice problem. And so I'm going to go ahead and erase these little details here. And now you could see that, okay, we're going to end up with, let's say, before the price change, if the price is going to decrease, right? I'm going to end up with one tangency here, which is going to describe my initial purchasing decisions for tacos and tequila. And then after the price change, if the price is lowered, I'm going to have a new optimal consumption bundle, right? So let's try to make this a nice color. So there's my new one, and here's my original one, right? And so I just want to focus for a minute on just the impact on X. I'd be going from, say this is my original amount of X, call it X0 star from my original price. And then the price is lowered and I purchase, presumably, right? I mean, I wouldn't know until I actually solved the problem, but presumably I purchased more X. So then I go to X1 star, right? So I'm trying to move these around a little bit better. So I purchased more X, right? And I have two different levels of utility. And so there you go. But hopefully you realize that this is one representation of the data, but I could just as well represent it on a demand curve as PX and the quantity of X, right? And then I would have 2 points on the demand curve. Remember, each of these purple points corresponds, and maybe I should make one of them a different color. Maybe that would help. So let me do that. Get rid of the purple one, and I'll make it dark blue. And each one of those points, the purple point corresponds to a higher price of X and a lower quantity. And so, and the blue one corresponds to a lower price of X and a higher quantity of X. And you see how the prices and the consumer choice problem are implicitly defined based on the description of the budget. But when we normally graph the Marshallian demand curve, then the price is explicit, right? So there's our X0. And so that's X0 star. And there's X1 star. Okay, so does that make sense? So you can use a consumer choice problem. If you knew the consumer's choice parameters, you knew their preference parameters for alpha and whatnot, and then you could predict how their choice of how many tacos to purchase is going to change as you change the price of tacos. And then you could graph that over on a demand function for that particular consumer. Because remember, for demand functions, even though we normally talk about market level demand functions, the market level demand function is just an aggregation adding up all of the individual demand functions for all the individuals in the market. And this, if you did this for each and every possible price, okay, you would end up with, and it's not necessarily a line, I'm just drawing it as a line, this ray, that it's straight. Normally they're not straight, normally they curve one direction or another. But this data in the consumer choice problem, if you solve a bunch of consumer choice problems with different prices, you end up describing what is called a price expansion path. And the price expansion path, and I can write it up over here, PEP is equal to price. And this is in your book too. Your book might call it a price consumption path because it's sometimes called that. The price expansion path has exactly all of the information that you need to construct a demand curve. So that's why we're doing this. So you understand where demand comes from. And there are actually some particular features about demand that we want to dig into, that in order to understand, we have to really understand the consumer choice problem well. So I'll ask one last question, because we're starting to run low on time, and I want to talk to you guys a little bit about Thursday. But is there anything that's unclear about what I've said so far, Arslan, Michael, why we're interested in this, and how the two problems relate to one another? Joshua, Michael, Barbie, anybody?
I think it's pretty clear the way you've explained it so far.
Okay, so now we know where demand comes from. Why do we need this more sophisticated sort of description of demand? Well, I mean, it gives us more tools for estimation. We can start to ask consumers surveys in different ways and things like that. But has anybody ever heard of upward sloping demand curves?
Oh yeah, like doesn't like luxury items do that, like Samsung phones and whatnot, and iPhones?
Okay, so I'm not gonna say what does and what doesn't, but I'll just say that does anybody find an upward sloping demand curve odd?
I wouldn't say odd, more like cringe.
Cringe. Well, you know what? See, Michael, we have this thing called the law of demand, right? And the law of demand says, as price goes down, quantity increases. As price goes up, quantity decreases. And an upward sloping demand curve defies that prediction, right?
Yeah.
Yeah, I mean, it does. It's supposed to be a law. I mean, if I tell you the universal law of gravitation tells you something about the force of attraction between two objects of certain masses, and then I say, oh, but it doesn't work sometimes. Doesn't that seem like a big flaw in your
because
science?
didn't you go over this before? Like, because you said that like most of economics assumes that consumers are like rational, right?
Yeah, and so you're getting kind of the nub of the question. When people have manifest upward sloping demand curves, so the price of something goes up, they want to purchase more of it. Are they being irrational?
Well, I like the term cringe, but you know, I guess
Well, you see, and now we have another way of examining that, because our observation before was that, and what I told you, you kind of had to take it on faith, but it is true. It's just that in this particular case, the methods for demonstrating it are beyond the scope of the course. We don't have the mathematical tools to do it. But if you have a rational preference relation, it generates a utility function. Now we have a utility function, we're solving the consumer optimization problem. So all of our consumers here are rational. So we eliminated that, strike. Now, can we get a rational consumer to generate an upward sloping demand curve? And the answer is yes, we can. And so consumers aren't necessarily behaving irrationally when they have upward sloping demand curves. But in order for us to understand when that phenomenon occurs, we have to dig a little bit deeper into what's going on. So so are there any last questions on this bit? I think Michael, you asked one question, which is like, okay, so what does alpha mean? I think it was you that asked that question.
Yeah.
Yeah. Well, there's another name for the Cobb-Douglas utility function that I prefer, because I don't like just labeling stuff with the names of dead people that first used it. Even though, as I may be one of those dead people someday, and people may look back and say, oh, the Hunter, utility function or something like that, right? If I win a Nobel Prize. But it's not very useful because it's not really descriptive, right? You know, Cobb and Douglas used it, but like, well, you know, so what? But the better name is the constant expenditure share utility function. Okay, so what you can show pretty easily, but I'll let you guys figure this out, is that if a consumer has Cobb-Douglas preferences, and so we said, you know, it's tacos to the 0.12, then when they're choosing their optimal consumption bundle, they will always spend 12% of their income on tacos and 88% of their income on tequila. And it's a really good question to ask, is that, you know, consistent? You know, how well do Cobb-Douglas preferences describe consumers? And I think there are a lot of people that would argue that they do describe the behavior of broad groups of consumers pretty well. You may know something like it's typical for the average American to spend about 40% of their income on housing, for example. And, you know, even as the income goes up, it's still about 40% of their income, and, you know, about 20% of their income on transportation, and about so much percentage of their income on other consumer items and stuff like that. So the thing that we'll probably talk about next time is that there's a way to extend the Cobb-Douglas utility function. So you're not talking just about two goods. You could talk about, you know, how we talked about categories. If you wanted to break things into categories like food and utilities and rent and stuff like that, you could have any number of goods you wanted. You could have 100,000 different goods if you wanted to, and still use Cobb-Douglas preferences. So Cobb-Douglas is very flexible, and it does describe some what you might call you know, common observations about the way that consumers behave. So Cobb-Douglas is pretty good. Okay, so if there are no other questions, then I want to talk a little bit about the exam. Okay, so I'm going to upload the exam cover page probably tomorrow, and everything will be ready to go. So we begin our exam at 8 a.m. and I'm going to give you until 9:20 to finish your submissions to Ignithium, and then I'll give you another half hour to upload your work to turn it in. So that's it. It's going to be basically what we did last time. I do want to talk a little bit, and obviously it was a sample exam, and almost everybody got, you know, a 9 or a 10 or even an 8. But the one thing I would encourage you to do is there's going to be a graphing problem, and to graph the graphing problem. And since it was a sample exam, I get it. Like, you know, not everybody, you know, was trying to do a super great job. But you want to do better on the graph because it's, you know, 15% of your grade, you know, label things and the rest of it. So give me just a second. I want to pull up an example of one that I liked, and let me do this. So for anybody out there who looks at this, and yours doesn't have to be the same as this. A lot of people got full points and didn't do exactly this. It is really helpful for me for you to paste the graph where I can see it at the beginning, because I compare all the graphs like at the same time. And if I have to go search for it, that just makes it more difficult for me to grade. You know, I might take a point off just because you didn't follow directions, even though I'm not going to hammer you. As long as you, like, a couple people, I think one person got full points and they just said, oh, my graph is down here. You know, technically that's okay. But again, just like a word to the wise, if you're ever you know, doing something for an exam, and I know you guys get pressed for time and the rest of it, but you do have your extra time where you could work on your graph while you're uploading your document. But you know, it's always a good idea to bear in mind that there's somebody, whether it's at work or it's here at school, there's somebody that's going to be evaluating and reviewing your work. And if you make things difficult on them, then, you know, that's a way to not get a promotion, or you know, you're making it more difficult for other people to reward you. So that's just a general comment. And okay. And you guys can ask me questions if you have questions about uploading the assignment or anything like that while I'm pulling this other one up.
Professor, so is the exam going to be like a mix of all the homeworks we've done, or one homework?
Yes, it's going to be a mix of all the ones that we've done, except for the math review.
Okay,
you know?
So 2, 3, and 4.
Yeah.
Okay. And you know how many questions it's going to be?
I think that there are about 20 on there. And let me see. Yeah, I think it's about 20.
Okay, so like 6 or 7 from each chapter, give or take.
Yeah, and other people would ask me before, and I think it's I'm waiting for it to load, so
okay.
I'll pull it up as a one. But if you see a question and you're like, oh gosh, this one is so simple, he's just asking me to identify the price. You know, the way the assignments are designed is to kind of like lead you into the more substantive material, the stuff that we're really interested in.
Mm-hmm.
And if you see a super simple question, there's a lower probability that it's going to be on the exam. So I would say, yeah, it's like, you know, 6 or 7 questions from each one, but probably the ones towards the end of the assignment that are more substantive are the ones that you're going to be responsible for. So, you know, I know some people would like say like, oh, well, you know, I got like half of these questions down and it's the first half, right? All the really simple questions, I nailed them, right? But you know, your expectation at that point in time is misaligned, because you know, those are probably not going to show up on the exam. So,
quick question, Professor.
Yeah.
Are any of the problems from this homework going to show up on the exam?
No. I mean, again, I think I've said this several times, but you have 3 exams and they're going to be 3 discrete sections. And the first one is on supply and demand. The second one's on the consumer choice stuff. The third one is on producer theory. They will not overlap. So
got it. Thank you.
So yeah, I mean, it's going to be from those assignments, the supply and demand, the taxes, and the price and these price floors. Those are the only questions.
So does that mean we're not going to have a cumulative final?
Nope. Sorry. You know, no cumulative final.
So, Professor, so when is the consumer choice homework going to be due?
So I'm guessing like maybe, like I said, we still have those last 2 problems. So probably at least to like Thursday of the next week.
Okay.
If we cover those 2 problems, I don't have any issue with giving you guys a little bit more time, but we'll just move on in the material like we've been doing here. You know, we're not going to wait. So at some point in time, you may have a little bit of extra work getting things done, but yeah, it's not right away. I don't know why this thing is taking so long to load. It was kind of doing this to me yesterday too. Okay, let me try one more time. I go out, I'm gonna come back in, and then see, I don't think it's gonna work on this one. Let's see. Yeah. Yeah, it's not gonna, well, maybe it'll load at some point. I don't know. But I'll just come back and check it periodically. Okay, but the main, like I said, comment was go ahead and make sure that you draw a nice graph. And there were one or two people that like forgot to turn in their assignment on Turnitin, and like you just can't do that. It's not optional. So, this is, the real exam for like big points coming up on Thursday. So don't, do something silly like that. You still have to do the two parts. You have to do the part on Ignithium, and then you have to do the part to submit your work on Turnitin.
How many points is it worth, Professor?
Well, so it's worth, so basically the way the course is designed is like 90% is on exams, and a third of that, is for each of the exams. So for your total grade in the course, it'll be worth 30% of your total grade. So 10% is homework and other stuff like our sample exam. So if you were to like count each homework and the sample exam, they're worth like maybe 2% each, and each exam is worth 30%. So,
okay.
Yeah. Okay. Yeah, it's still not loading. So I don't know. Cal Poly IT. Okay. So I don't know if anybody has any questions for me. The other thing is, like I said, there was one person that didn't actually submit their questions from Ignithium. They didn't like copy them and paste them in. And, that will get you 0 points. So, don't do that, and do a nice graph. And, I wanted to give you guys an example of a nice graph, but from somebody else's work. But, do your axis labels, label important points. Usually it's important to label the intercept terms. Like if you got a line and it's crossing the vertical axis, label the vertical axis, and sometimes you label the horizontal axis. It depends. But as long as everything is presented clearly, more information is better. So, but obviously it's a matter of like discretion, as long as you're communicating clearly. That's the goal, and you don't have to put everything on there. But yeah, more is better. You know, so you just have to be reasonable. And it's nice to have colored graphs too, to the extent that the colors are meaningful, right? Again, you always want to think that you're trying to present your best work. So, as long as you have that in mind, you have the right idea. So this is our last minute. Any final questions?
Yeah, so you'll give us the access code on Thursday morning, Professor?
Yeah. So at 7:45 a.m., I will be emailing access codes and making sure everything's ready for you. And then I'll, open up my Zoom meeting and you guys can join. Like I said, I'm just there to answer questions. If you don't want to join Zoom, you don't have to, but just in case you get stuck on something. And then what sometimes people do to me is they're like, oh, like I have a rendering problem here and I don't know, should I use a substitute exam question on this one? And sometimes I can help with that. It depends. Every once in a while, I have somebody ask me and it's something that they should know. So I'm not going to tell you, like if your alpha is out of range, that's something you should know. So I won't say, I'll just say, well, you have to use your best judgment, what you think. It doesn't mean you're wrong or right if you were going to or you weren't. It just, but every once in a while, you get the double negatives or, you get a 0 or something like that. And somebody say like, well, this one doesn't look right to me. And I'll say, yeah, I would use the substitute exam question for that one. But like I said, it kind of depends, because if it's something that you're supposed to know, then I won't say. One of the ones that people have asked me in the past is, sometimes you get an example from Ignithium where the price floor, the price ceiling is binding or not binding. And they might think, well, oh, if it's not binding, then I should use a substitute question. And there's nothing wrong with that question. So, that just because it's not binding doesn't mean it can't be answered, and if you've gone through the examples on Ignithium and you've never gotten a non-binding example, like I said, for my, experiences, it's like about 1 in 4, then, you might want to make sure you understand what's happening with non-binding price ceilings and price floors, and, practice a little bit more. Okay, so that's it for me. I'm stopping recording.